So every once in a while I get a question about symmetry versus position. Now to start off, symmetry is no longer in the GD&T universe. It's been taken out of the 2018 standard. You can use it if you're making drawings to the 2009 and earlier versions. So it's not currently allowed if you're using the latest standard, but because you're not forced to update ASME Y14.5 standards, you could be using 2009 or 1994, in which case symmetry and concentricity are available. So what is symmetry? Symmetry, unlike concentricity, is for essentially width features. So concentricity you would use for typically cylindrical features. Symmetry is mostly going to be for tabs, slots, things like that. So on this part, I've shown an internal width feature. We've got a simple datum reference frame, a plus or minus dimension. With symmetry, you're limited to a plus or minus dimension. If you wanted to use a basic dimension, you'd have to use profile. So symmetry is going to control a feature of size, similar to position. Now, what is the difference between symmetry and position? They're very, very similar. In both cases, in this example, we've got a tolerance zone that's the distance between two planes that's 20 thousandths apart. It's going to be centered on the true position given by a basic dimension. Now, often if you see a symmetric part, if datum B itself is a feature of size, it may be, you have a datum plane going through the center of the part, there may be no basic dimension. That would mean it's an implied 0 basic dimension, but for here, I've just made it explicit. Now, the tolerance zone is right here. With position, we've got to find the center plane of the unrelated actual mating envelope and see if that's within the tolerance zone. So what does that entail? Here's an extreme version of a unrelated actual mating envelope. So it's two parallel planes that expand to capture the feature. We've got a center plane, right, that comes from the unrelated actual mating envelope, and that center plane should be within this tolerance zone. Of course, this one would fail miserably, but that is the idea. You're looking for the high points on the surface to locate the feature. Now, it's still got to be within the limits of size. That's a separate check, and that's kind of a rule number 1 check. You got to go in there and make sure that's okay. But position will basically ignore something like this, right? If you have a large void, as long as it's still within the limits of size, it really doesn't affect where the center plane is. I hope you can see that. Now, the other advantage with position is we can use maximum material condition. We could set the tolerance at maximum material condition, and we can have our datum references at maximum material condition. With symmetry, we can do neither, right? Our tolerance needs to be at regardless of feature size, and our datum references need to be at regardless of feature size, or the tolerance doesn't really make sense. So, symmetry. We're going to control opposed median points. So what that means, here's our feature. At this distance, right, we'll say right here, we check this point and this point, find the center. Right? We go in some distance, find the opposing points, and find the center. Now, I'm drawing it in 2 dimensions, but this would happen in 3 dimensions. This is different than just saying, I'll just run an indicator and get the high or the low reading. You've got to get this point and the opposing point. Now, on a practical matter, what you would need to do with an indicator, because indicators have preload, right? You set it right here, or you set it on your basic dimension, you get a measurement here, and you've got to record how far you go in for the next measurement, say 100 thousandths. Record, 300 thousandths in, 400 thousandths, whatever. Write those numbers down, for, one plane, okay? Come in here, so the 1 inch, do the bottom, right? Record at 0, 100, 200, 300, etc. And then compare those numbers and see how far they are off. That'll give you where the center is, right? It'll tell you if you have a void, say right here, it would move this center up a little bit. Okay. Now, I've never seen anybody do this on a surface plate. I've seen illustrations of people doing it on a surface plate. Never seen it in real life. If you've ever done it in real life, leave me a comment in the leave me a comment down below. Okay. So to make it clear, this is 2 dimensions. The part would have depth, so you'd have to do that here, move it in a little bit, do it at another spot, move it in, do it at another spot, while also keeping track of how far you're going in this way. Okay. How many points? I don't know. I mean, whatever makes you comfortable. But what you're looking for is areas like this. Now, one odd thing with symmetry, say, here's our tolerance zone inside of the part. All those median points need to be within that tolerance zone. Say this bump right here shifted 1 point outside of the tolerance zone, right? Now we're out of tolerance. But if there's a similar bump opposite that, now we're back in tolerance. Okay? With position, none of this would matter at all, right? Because in this example, our unrelated axial mating envelope would just ignore what's going on here, although it would not ignore it if it went inside of the part. Okay. Make it clear, you still got to meet your limits of size here. So this deviation, say this was at MMC size, that deviation couldn't be more than whatever your tolerance is going inside of the part. Now, what makes symmetry odd is that right now, in this given example, symmetry and position would give you essentially the same answer. But if I shift that defect this way, now I've got 1 point off here, and I'm going to have another point off here. But if I checked it for position with the unrelated axial mating envelope, this has no effect, okay? No effect at all. So I would, in my opinion, symmetry, I've never seen a situation where it really needed to be used, where you couldn't use position and profile and some other geometric controls. I think there are situations where concentricity could be useful. So concentricity, the idea is like the balance of mass. So if you did have parts that spin, it makes some more sense. I could see how there'd be a useful purpose for that. Here, I've just never seen an application. If you have, please let me know in the comments down below. But I think that's the best way I can explain it, right? I don't want to go into too much detail because, again, not something you see on drawings very often. But if you do see it on a drawing and you disagree and you think it should be positioned, hopefully this gives you a little bit of ammunition to make your case. Again, it's been dropped from the 2018 standard. A lot of drawings today are still made with the 2009 standard, in which this is an option that you can use. Position, most of the time, will give you the same thing. Okay. So that's the end of this video. If you enjoyed it, please like and subscribe. Leave a comment down below.